Okay, what we've got here is a ball. Somebody releases it from the bottom of a bucket of water, and they time how long it takes to get to the top, where the distance it has to get to the top is a known value, a known distance. I'll call it X max. I'll call it X final. Where we know the distance because they gave us the depth of the water. I'll call that H as 32.7 centimeters. I think I want to write that as 0.327 meters. And they gave us the diameter of the ball. The diameter of the ball is 0.02587, capital D, I'll call that 0.02587 meters. So X sub F, this distance right in here, is equal to H minus D, which is just 0.327 meters minus 0.02587 meters. And that's our X sub F. That's where I can say it. 0.327 minus 0.02587 is what I got up here. So hit an enter on that, and I get 0.3011. 0.3011 meters for X sub F. Alright. So what we're saying is you release the ball and it gets to the surface having traveled a distance of 0.3011 meters in 2.38 seconds. And we're supposed to find out what C is, which represents a coefficient of viscosity of the water, creating this retarding force on the ball. So, this would be a rather straightforward problem to find out how fast it's going, for instance, if the speed was constant, or it'd be pretty easy if the acceleration was constant, but we've got a force that depends on how fast the ball is going, and so clearly the acceleration is not going to be a constant. So let's see if we can get an expression for the acceleration, and then we'll be able to use our numerical methods to find out how express for some given value of C how long it takes to get to the top, and play around with C until it takes 2.38 seconds to get to the top. Or actually, I think what I'll do is I'll give it 2.38 seconds, see how far it gets, and then adjust C until it only gets 0.3011 meters. And I'm calling that upward. I'm calling this my x-axis. This is my x direction, and this is my start line right here, the origin for my reference frame. Okay, I think I got a plan. We got to get an expression for the acceleration, and we'll get that from Newton's second law. We've got a buoyant force acting in the upward direction. We've got, I think I'll call that F sub B. We've got a weight force acting in the downward direction. I'll call that the gravitational force. I'll call it F sub G. Just mg. Typically call it W, but I think I'll go with F sub G here. F sub B, we'll work on that. But also in the downward direction, I've got this retarding force. So it's assumed rubber ball. I expect it to bob to the surface, so the buoyant force is going to be greater than the weight. And to start off with, it's going to start moving upward, but the faster it's moving upward, the greater this force. Initially it's 0 because the velocity will be 0, so there'll be no force in the downward direction. I think I'll just leave this buoyant force as is there, and say we'll call upward the positive direction for acceleration. Alright, so let's go. Sum of the forces in the upward direction is equal to the mass of the ball times the acceleration in the upward direction, which will just be the buoyant force minus that viscous force minus the gravitational force, and that's equal to the mass times the acceleration. The buoyant force, it's in magnitude, it's the weight of that amount of water that would be where the object is if the object wasn't there. So I'm going to call it m sub w times g, where this w is a fictitious amount of water. It's how much water would fit right into this spherical region where the ball is actually taking up space. And then minus that viscous force, we say, is just c times v, and then minus the weight force acting on the ball, mass of the ball times g, and that's equal to the mass of the ball times the acceleration experienced by the ball. Okay, the mass of anything, the mass of that amount of water can be expressed as its density times its volume. Now it's actually the volume of water that would fit where the ball is, but that's going to be equal to the volume of the ball. So I can stick that in here for mw, and I get rho w vb. I think I'm going to switch the order here. Subtract that's times g. Well, I should do pure substitution, so let's not switch the order yet. Equals ma. Then I'll divide both sides by m and switch the order. So I'll have a is equal to, I'm dividing both sides by m. Actually, maybe it'll be easier if I go ahead and write that in every place. That's what I'm doing. Might as well express it that way. So then a is just equal to rho w v b over m, all times g is that first term. Then I'm going to write the last term, minus g, and then minus c over m times v is this middle term. I'm going to factor out the g from these first two and write this as rho w vb. I think these are, density of water is known. I always memorize it as gram per centimeter cubed, but that's equivalent to 1,000 kilograms per meter cubed. And divided by the mass of the ball, and then minus 1, and factoring this g out, minus c over m times v. So I got a relationship between the acceleration of the ball and the velocity of the ball. Looks like the greater the velocity, the smaller the acceleration. It involves the c, which is what I'm looking for, so I can't substitute anything for it, but this piece has all known stuff in it. I think I'll define that as a sub c for a constant. It's the constant term of the acceleration, and then I got to subtract off a part that depends on v. So by definition, a sub c is equal to rho w vb. I've just defined it that way. M minus 1 all times g. You can think of that as a sub g, the acceleration due to gravity. So a is equal to a sub c. I'm sorry. I want to go ahead and evaluate that. A sub c, indent that just a little bit. I'm worried about running out of room. Let's see how small I can write. It's equal to 1,000 kilogram per meter cubed, there's the density of the water, times the volume of the ball. I think I'd to cut down on how much stuff I got to substitute. I think I'd like to go ahead and solve for that separately. It's got a diameter of 0.02587. meters. Now, the way I got the volume of a ball memorized is the volume of a ball or a sphere is 4/3 pi times the radius of the thing cubed, but the radius is just d over 2, so it's VB is 4/3 pi times d over 2 all cubed. Alright, 2 cubed is 8, so I've got an 8 in the denominator. 4 divided by 8 is a half, so it's pi over 6 times d cubed. Or the volume of the ball, I'm emphasizing that it's a capital V here because I got a small v for velocity in the same problem, is pi over 6 times 0.0258 meters all cubed. So let's see what that turns out to be. We've got pi divided by 6, and all that times 0.0258. Is that what they gave us? 7.2587. meters all cubed. 0.0257 to the 3. Enter, and I'm getting 9.0654 times 10 to the minus 6. And meters cubed for V sub B. And that's the value that I need in here. For V sub B right there. That's what I'm substituting. Okay, so V sub B 9.0654 times 10 to the minus 6 meters cubed. And then all that's got to be divided by the mass of the ball, which is 0.008488. kilograms. And then minus 1 and times 9.80 meters per second squared. And let's go ahead and evaluate that. So slide this down a little bit so I can see it. And I get, it's 1,000 times 9.0654 to the times 10 to the minus 6. And then all of that, I think I'll put that in, I think I can just hit minus 1. Let's go minus 1, and then put all of that in parentheses, and times 9.8. Enter, and I'm getting a negative value. So I don't actually buy that this is such a small number. Oh, I see what it is. I've forgotten to divide part of it, so I'm going to try to double click on that and get that in here. I got to divide by the 0.008, so I'll take this piece right in here, right before the -1. That makes it look better anyway. So divided by 0.00848. Hit enter there, and I'm getting 0.6765. I'll try that one more time because I left off one of the 8's here. Hit enter again, I get 0.6666, 4 6's there. So A sub c, this constant term, is 0.6666, and that should come out to be meters per second squared. Let's check that. I got meters cubed times 1 over meters cubed cancels, the kilograms cancel. So this whole thing in parentheses is unitless, -1, which is unitless, but multiplying it all times something with units of meters per second squared, so I'm all set there. So I want to, I'm going to write down this expression up here one more time, where I'm using this definition. So this whole first piece I'm just calling A sub c. So the acceleration expression that I need is A sub c minus just the c over m times v. So that's what I got to evaluate, where the A sub c value is right there. Alright, I think we're ready to go ahead and start solving the numerical problem. Use that idea of figure out where it is at one instant, and use such a small time interval that at the next instant we can just use the basic definition of things like acceleration and velocity. So the new position is of the current velocity, or the velocity appropriate for the time interval, times the length of the time interval, but is a small time interval, so it works. So for instance, my usual thing is have an integer counter that goes up through some large number of values, and I think I'll space that out just a little bit more in case I need a couple of lines on writing it. 1, 2, and then the clock reading I'll let be n times delta t, where delta t is going to start out with some, I might have to play around with that, but delta t, arbitrarily small number. I'll make it some small number to start with. I like to specify a value, even if I don't wind up using that, just so what delta t means is pretty clear. And then all of these will just be the same thing. The next few lines will be whatever I put in there. So the clock is running, starts out at time 0, and then increases. I need to know where it's at. I mean, this is the important thing. I want to find out. I'm going to rig things up so it's at the top at the specified time, 2.38 seconds, I think it was. Yeah, 2.38 seconds. So x is going to be, what we use is, well, it's initially at time 0. Let's just write that as is. And then x sub n, like x1, will be the previous x, so I'll call that x sub n minus 1. In this case it'll just be the 0, but it's the previous one plus the velocity that's appropriate for the time interval from 0 to 1. From n is equal to 0 up to n is equal to 1. I'll call that the velocity at n minus a half. So when n is 1 is the velocity at n is equal to a half, velocity at a half for my integer counter, which I let take on half integer values, and then times whatever the delta t is. I'm going to try to write that a little bit smaller there. So got a lot of things to write here. The velocity, I'll call upward the positive direction. So positive sign for velocity means upward. So for this, it's just one-dimensional motion. I can characterize the direction with just an algebraic sign. It starts out at 0 because they release it from rest. The velocity at time n times delta t when n is equal to 1 is going to be equal to the previous velocity. So n minus 1 plus the acceleration that's appropriate for n is equal to 0 to n is equal to 1. So it would be like this one minus a half, which is the same thing as this one plus a half. So I'll call it, I'm on n, so I'll say it's n minus 1 half. And then times the delta t. Alright. And then I'm calling this t sub n, x sub n, v sub n. Call this a sub n. It starts out at whatever this turns out to be. It uses the c in there, so I'm going to need that. C is equal to, I'm going to set it equal to 0 to start with, but recognize this is something that changes. I'll be playing with that. Looks like I'm going to be using the m in there as well, so I write down what the mass is. I think it's 0.0084888 kilograms, but I want to look that up. So I'll go all the way to the top. Yeah, 8.488 times 10 to the minus 3 kilograms, which is just what I wrote. So I do need that mass, and then I'm working on this a sub n. So it is in general a sub c, so I need that value as well. A sub c, go slide this stuff down. Try to go pretty quickly. Make a little bit more room there. A sub c is equal to, we just found a value, 0.6666 meters per second squared. Okay, so this is a sub c minus c over m times v sub n, whichever one I'm working on right now. So in this case, that would be the 0 right there. And then for the next one, I just have to copy that down. No, the next time it'll be using this velocity, whatever's right here, but I'm just copying that one down. I'm going to try to draw a row line here. Okay, what else do we need? We use this v n minus a half in here, so I'm going to need that v sub n plus a half, I'll call it. So when I'm working on the 0, that would be this cell right here. And this is the one where it's the getting started thing. So I like to use an acceleration during the middle of the time interval, but I'm going to use it, the one at the start of the time interval for this, because that's all I have. So it will be this 0 plus a sub n times delta t over 2. That'll give me a good approximation to the velocity at time 1/2 times delta t. Okay, and then I need a sub n plus a half. So for the time 0, that would be at n is equal to just a half, so we're at half of delta t. And it'll just be this same expression that I got there. So a sub c minus c over m times vn plus 1/2, this v value right here. Alright, that's for time 0. For the next time in here, this is actually where I need an expression. This will be vn minus 1/2, in other words, this value right here, plus, and then it's going to be the acceleration from that's valid from midway between these two up to midway between these two. So from 0 to 1, it's like from a half up to 1.5, for instance. So it's going to be, during that time it'll be this a sub n and then times the delta t. So this is a plus sign. Hopefully I'll be able to read that when the time comes. And then this one is the same thing as up there. I'll just be using this velocity to the left of it. Okay, I think pretty well set to go ahead and put this into the spreadsheet program. Let's see if, yeah, let's go ahead and do that. So I'm going to call this the end of part 1, because, well, this is just going to be the same expression. That'll be the same. That's clearly the same. And then this one I've got figured out. So it'll just be the same kind of expression with, using the neighboring elements. And then the rest of the spreadsheet, this will all just be copied down. So let's call that the end of part 1. And we'll pick up on the spreadsheet part. We'll call that part 2.